Okay, so hi everybody. I'm going to tell you about a joint result with Charlie Carlson, Alex Gola, and Luca, which grew out of a question that Luca asked us in 2017 during the Bridging Continuous and Discrete Optimization program at Simons. And the question is about lower bounds on the size of a data structure that can answer queries about the sizes of cuts in a graph, approximately. And this work has a feature that this is it's the shortest paper I've ever been a co-author on. It's 8 pages long, and the proof is incredibly short and self-contained. And I'll try to tell you the whole proof in this talk. Okay, so the basic object that we'll study in this talk is called a spectral sketching scheme. So that's an algorithm which takes as input an n-vertex undirected unweighted graph and a parameter epsilon, and it outputs a function from Rn to R, f, which satisfies the following guarantee. For every vector x in Rn, f of x is multiplicatively close to the Laplacian quadratic form of the graph G. So L is the Laplacian matrix of the graph, and what we want is for every x, f of x is between 1 plus or minus epsilon times x transpose Lx. So this function f, really the algorithm should output some, description of the function f, some way of storing it with some number of bits, and this number of bits is the size of f. And f is really just a data structure for answering these types of queries, but all we care about is the size of the data structure. We don't care about the query time, we don't care about other features of the data structure. And the motivation for studying this particular problem is that it includes, as a special case, cut queries. So when these vectors x are indicator vectors of subsets of the vertices, then the Laplacian quadratic form is simply the weight of a cut in the graph. So in particular, if you have a spectral sketching scheme, you have a way of producing a data structure that can answer queries about the sizes of all cuts in a graph up to this 1 plus or minus epsilon factor. And so the question we're interested in is, what is the smallest possible size of a spectral sketching scheme as a function of n, the number of vertices, and of epsilon, the approximation parameter? How many bits do we need to sketch all of the Laplacian quadratic forms in a graph? And what was known about this at the time when we started this work? Well, there was an upper bound of n log n over epsilon squared bits, and this followed from results on spectral sparsification due to Batson, Spielman, and myself, in which we showed that for every graph G, there's some other weighted graph H, so that the Laplacian quadratic form of H, 1 plus or minus epsilon, approximates the Laplacian quadratic form of G, and H has only n over epsilon squared edges, order n over epsilon squared edges. But this was a weighted graph, so you need an extra log n bits to discretize the weights, and that yields a spectral sketching scheme with n log n over epsilon squared bits. So that's the upper bound. On the other hand, the lower bound at the time was a result of Andoni, Chen, Krautkammer, Chin, and Woodruff, who showed that every scheme for doing this requires omega n over epsilon squared bits. So there is this gap of log n between these two bounds. That's not a very big gap, but we found the conceptual question interesting. The conceptual question is, can you somehow do better for sketching the cuts or Laplacian quadratic forms of a graph if you have a data structure that's not a graph? So this is a question that Luca raised during the semester, and we were able to prove this theorem about it, which is that indeed any spectral sketching scheme of any type, doesn't have to be a graph, must use at least n log n over epsilon squared bits, provided epsilon is not too small. It has to be at least 1 over poly n for this particular exponent. And further, we actually proved that this is true even if you only want a sketching scheme that works for 0, 1 vectors. So it only sketches the cuts of the graph, not all of the Laplacian quadratic forms. And so what that says conceptually is that you can't do better than spectral sparsification, even if you allow yourself to use data structures that don't come from graphs. So I'll tell you the proof of this, which is very short. The proof is based on this key lemma is called the rigidity lemma. And here's what it says. If you have two undirected, unweighted deregular graphs, G and H, on the same vertex set, 1 through n, with the property that their Laplacian quadratic forms are 1 plus epsilon multiplicatively close for all real vectors, So this is the notion of spectral sparsification introduced by Spielman and Tang. Then, provided epsilon is small enough, uh, these two graphs actually have to have a lot of edges in common. So literally, the intersection of the edge set of H and the edge set of G has to be of size order n. And the bound here is dn over 2, that's just the total number of edges of a d-regular graph in n vertices, times this factor 1 minus epsilon squared d divided by 2. So you'll notice that this lemma is vacuous when epsilon is bigger than square root 2 over square root d, because the right-hand side is just 0 or negative. But then suddenly, if you reduce the error down to 1 over square root d, the behavior changes completely. Then the right-hand side becomes a constant, and the lemma is now telling us that these two graphs, if they're 1 over square root d spectrally close, have to share a constant fraction of their edges, which is a very strong property. I mean, these are sparse graphs, and you don't expect, if they're just random, that they would share a constant fraction of edges. Now, this kind of sharp transition in what the lemma says is not an accident. It's actually necessary. It's necessary because if you take two random d-regular graphs G and H, they actually always epsilon approximate each other for epsilon equals 2 over square root d. So this is a number that's related to the Alon-Bopana bound, and this result follows from Friedman's proof of Alon's conjecture about the spectrum of random d-regular graphs. So there's this very sudden change in behavior. If you have epsilon 2 over square root d, or bigger than, if you have epsilon 2 over square root d, then all d-regular, or most pairs of d-regular graphs spectrally approximate each other. But as you go down to 1 over square root d, then suddenly it becomes a very rigid condition, and the graphs actually have to be combinatorially very close. So I won't prove this for you. The proof is a 2 or 3 line exercise in linear algebra, and I encourage you to do this exercise if you want to learn something neat in spectral graph theory. I'm sure Luca would have enjoyed that. And a hint is pass through the adjacency matrix and consider the Frobenius norm of the two of the difference between the adjacency matrices. Okay, so let's say we have this rigidity lemma. Let's now see how it implies the proof of the main theorem. So here's the proof of the theorem. Suppose we're given n, a number of vertices, and an approximation parameter epsilon, and we want to prove that any spectral sketching scheme for epsilon approximations, spectral approximations of graphs on n vertices, must have at least n over epsilon squared edges. Okay, so now we're going to choose a degree d so that epsilon is less than 1 over 3 square root d. Okay, so d is like 9 over epsilon squared. Okay, and now we're going to consider the following exponentially sized graph, which I'm going to call x sub epsilon. The graph is defined as follows. So its vertices are its vertex set is the set of all d-regular graphs on n vertices. So the number of d-regular graphs on n vertices is about 2 to the dn log n over 2, and so the vertex set of this graph x sub epsilon has that exponential size. The adjacency relation in this graph is given by 1 plus or minus epsilon spectral approximation. That is, two graphs G1 and G2 are adjacent in x sub epsilon if and only if the Laplacian of G2 is a 1 plus or minus epsilon approximation of the Laplacian of G1. And you can see that this is a symmetric relation, so this defines an undirected graph x sub epsilon. Okay, so what does the rigidity lemma tell us about this graph x sub epsilon? Well, it turns out it gives us a strong bound on the maximum degree of this graph. Now, why is that? So consider a vertex in x sub epsilon, that's just a d-regular graph. Now, some other, let's call that graph G. Another graph H is a neighbor of G if and only if H 1 plus or minus epsilon spectrally approximates G for this particular factor, approximation factor epsilon, which is less than 1 over 3 squared d. So that's the regime in which the rigidity lemma applies. And what the rigidity lemma says is that this neighbor H must actually share a large constant fraction of edges with G. and that fraction is 1 minus epsilon squared d divided by 2. What that means is that this neighbor h, most of its edges are just edges of G. The number of free edges that it has is actually something like epsilon squared d squared n, so a small number of free edges. And that implies that the number of neighbors is at most 2 to the epsilon squared d squared n log n plus some lower order terms, roughly. So this graph x of epsilon has small degree. Okay, if it has small maximum degree, it has to have a large independent set. So it has an independent set of size at least the number of vertices divided by the maximum degree, which is 2 to the half minus epsilon squared d times dn log n, and that is just 2 to the omega dn log n for some other constant because of the way we've chosen epsilon. Okay, so this graph that we've constructed has a large independent set. Now, what's the punchline? Well, the punchline is that if you look at any two graphs in this independent set, so called the independent set Y, they do not spectrally approximate each other up to this factor epsilon. And as a result, no two graphs in this independent set can share an epsilon over 2 spectral sketch because of roughly the triangle inequality. If there was such a spectral sketch, then the two graphs would both be close to the sketch spectrally, and then they would be close to each other. But that's not the case because it's an independent set. So what's the conclusion? Well, the number of distinct spectral sketches must be at least the size of this independent set, and that's 2 to the omega dn log n. But remember, d is 9 over epsilon squared, and so we've just proven that there are 2 to the omega n log n over epsilon squared distinct spectral sketches, and that completes the proof. That means that the number of bits in a spectral sketch is at least n log n over epsilon squared. That's it. That's the whole proof. That completes the proof of the first line in the theorem. Any spectral sketching scheme has to use n log n over epsilon squared bits. And in the paper, we proved that this is true even if you restrict to 0, 1 vectors, that is cut vectors. And it's kind of amazing during this collaboration. As soon as we proved the spectral result, it was literally within minutes that Luca found a proof that would work for cuts by replacing the rigidity lemma by one for cuts that involves a very nice Gomez-Williamson style rounding scheme. So that's in the paper if you're curious about that. So that's all I want to say about the result, and I want to end the talk by saying that I really miss Luca. So I of course miss him as a scientist and as a teacher. I learned from him at every stage of my career, and I tried to emulate his clarity. But I especially miss him as a person. He was very generous to me. The first time he emailed me was asking for a SciComp review when I was a postdoc. And at the end of the email, he also invited me to meet him for coffee near Dolores Park, and he spent hours talking to me. Later, when he invited me to his house, he offered to drive me to and from the park as part of the invitation. We had many delicious meals over the years with Luca, Junes, Alex, and others, and it was a really delightful mix of working and not working together. And when I visited Bocconi, I could see that Luca had created this a wonderful culture there where the graduate students felt very cared for by the faculty. I hope that we can keep Luca's way of being alive in our community, and thank you, Luca.